Welcome back to the Mechanics of Solids lecture series. In this video, we're evaluating beam deflections by the superposition method using the beam tables. The lesson objectives are to evaluate the beam deflection at a specified location using beam deflection tables and the superposition method. Here's an example. We're asked to evaluate the deflection at the cantilevered end, point C, using the deflection table. Right here is what we're looking for. Quick sketch of the deflected shape. We imagine it might do something like that. I chose this example because it's a good example that illustrates the complexities that can be encountered when applying the superposition method. Basically, the deflection at C is going to be calculated by superposing three different cases. And this is what those cases are. Case 1 is the result of the load acting over the cantilevered end. So I'll sketch the load in W naught right there. We're going to assume for the moment that we have a fixed support right here. In other words, we're not going to consider the rotation at joint B. We want to consider purely the effect of the deflection of that cantilevered end, which if I sketch it would look something like that. Let's call that deflection V1C. Case 2 also results from the load over the end of the beam. But this time, what we want to find is the effect of that load on the rotation of the joint. And basically, the load on the end causes an equivalent moment at the joint equal to WL squared over 2. Okay, we could solve that by making a cut, calculating the reaction, and then turn around and superposing it on the joint here. That moment is going to cause the beam to rotate about the joint in the clockwise direction, and therefore we get an effect that looks something like that. Now in this case, I'm not going to worry about the deflection. I'm just going to simply consider the rotation and draw this out as a rigid extension of the rotation. So we're just finding the effect of the rotation as if there were no load on the end of the beam. We've already considered the load in the first case. We'll call this one V2C. Finally, case 3, we consider the contribution of the uniform load between points A and B. This is W. This will also cause rotation at joint B, but in the opposite direction. If we didn't have the cantilevered end at all, the deflected shape would look something like that. So this time, we'll take the rigid extension of the end, but it's going to be in the positive direction. And I'll call that deflection V3C. Okay, so the total deflection VC is going to be the sum of those three cases, V1C plus V2C plus V3C. And we can find each of them by looking them up in the beam tables. Case 1 is a uniform load on a cantilever beam. So we want to go to the cantilever beam table and find the end or peak deflection. Simply supported. These ones are the cantilevered, and here's the one we're looking for. Uniform load over a cantilever beam. The maximum deflection, WL to the 4th over 8EI. So we'll write that in. V1C equals negative WL to the 4th over 8EI. It is in the negative direction. Case 2, we want to find the rotation at the end of a simply supported beam due to an applied moment. This is one of the simply supported load cases. And here's the table that we're looking for. Aha, this is the one we want, an applied moment at the end. And we want to find the rotation at the same end of the applied moment. Here that's called theta 1. And this tells us that theta 1 is equal to ml over 3EI. For the moment, I won't worry about the sign. So theta at B is equal to ml over 3EI, where m is equal to WL squared over 2. So this becomes WL cubed over 3 times 2 6EI. V2C is equal to theta times the length of the cantilevered end equals WL to the fourth over 6EI, and it's also negative by inspection. Case 3 is also a simply supported load case, and we want the rotation at NB. So we're looking for a uniform load, that's this case right here, and we want the rotation. Note that they're equal, so theta 1 equals theta 2, WL cubed over 24EI. So theta B is WL cubed over 24EI. Then V3C is theta B times L equals WL to the fourth over 24EI, and this time it's upward or positive by inspection. Okay, so we need to add these terms together. This one, and this one. Note that they all are multiplied by WL to the fourth over EI, so I can pull that out, WL to the fourth over EI, and I am left with V1C a negative 1/8 minus, for V2C 1/6, then for V3 1/24. My least common multiple is 24. I'll multiply this by 3 over 3, this by 4 over 4, and what I'm left with here is negative 3 minus 4 plus 1, which is negative 6 over 24, or negative 1/4. Therefore, my deflection is WL to the fourth over 4EI. That concludes this example.